All right, so we welcome everybody. Thanks for taking time to come in. And always a little bit difficult to coordinate these things when we're doing it half from afar. So hopefully this will go pretty smoothly. And bear with us if there are any technical difficulties. How's the audio?
Good. Sounds good. Good.
Good. All right, great. So you've all gotten a copy of the proposal. So the way that we'll proceed here is Earl's got about half an hour's worth of slides to go over to kind of present the topics, and then we can talk about any questions or issues that you might have after that.
Sounds good. Okay.
All right. So Earl, I'm going to share the screen. Just let me know when you want to advance the slides, okay?
Okay, actually, I think if you share it, I can control it from this side, too. Really? Like when you share it, it says request control, so I can, if you pop it back up, I will request remote control. Yep, request. And
all right.
Cool. All right, let me make sure it's working. Let's see. No. Okay, well, oh, so it's mouse control. Okay, go back up. Okay, mouse control. Well, thank you all for being here. Thank you for your advice, support, and patience, I guess you'd say. This is going to be my presentation. As you saw in the proposal I sent out for you guys, my theme is unmanned aerial vehicle-based measurements of the urban forest. Okay, a little bit of background. Urban forest. Plain and simple, an urban forest is all the trees within the public and private trees within a urban area. This is a very dynamic system. Trees change in and out. One of the things that's very important with this is the average half-life of a tree on the street side area is only about 13 to 20 years. So these change out very, very frequently. So for DeKalb itself, every 5 years, 2,200 trees or so will need to either be replaced or removed. So that's a lot of turnover in a system. For management of this, it does require that you have a good inventory of this system. So we need to keep these inventories current, comprehensive, well filled out. There are lots of information factors that can be needed. They are usually type of tree, number of those trees, and their distribution. And also what they want to know lots of times is the health, size, and age of those trees. Oh, there we go. That's good. There we go. Oh, I can use the keys. Okay, excellent. So, to get these inventories, you need to survey these resources. Typically, this has been done through the time-honored tradition of the manual field-based survey. People going out in the field using the good old-fashioned either tree poles or hypsometric measuring, but it takes a lot of time to go out there and measure all these trees. They are very, very comprehensive, but because it takes so much time, these can't be done frequently. So there's very low temporal resolution. A new remote sensing technique that has become popularly used is the airborne laser scanning. But the problem is it's contracted. It takes a lot of money to do these things. It also has low temporal resolution because if you're shelling out a lot of money to do this, most agencies don't have that in their budget to use on a constant basis. And it does have difficulty resolving small features. So here is actually just an example of what you get from an LAS or ALS. The top is just a zoomed out area. And it looks like you have some features in there, but when you zoom in, you start seeing pixelation coming in. We'll talk about the actual resolution of that in a little bit. But while that looks kind of good now, we'll actually find out that it's not as good as it should be. So what I'm proposing is using the use of unmanned aerial vehicles to do these surveys for the inventories. These do have relatively low cost. There's lots of those consumer grade units out there now that anybody can buy, which is what I've done. I've bought my own, and they have really good imaging capabilities now. The megapixel ratings of these things are constantly increasing. They're very easy to operate. They can be used for any size area. You can use small plots if you need to do a spot survey, or you can do larger plots, larger surveys. They can be deployed very quickly. You can just take your one out there. If it's charged, go, do what you need to do. There's not a lot of build-up time. There's not a lot of organizational time taken for this. And the best thing is, you can take this aerial imagery and you can process it to generate your tree data. And this is done through photogrammetry and then an advanced form of photogrammetry structure from Notion, which we will talk about here in a moment. Okay, so my basic research question is, are unmanned aerial vehicles, vehicle-based urban forest tree height and trunk diameter estimates more accurate compared to the airborne laser scanning and the ground-based field survey generated results? Basically, can we use this UAS to do as well, if not better, than the other methods currently employed? To go along with this, we've got a couple subtopics that I feel need to be addressed. Within this are a couple conditions. One, the leaf on versus leaf off condition of the trees. What is better for different things? On this, I have the idea that the leaf off would actually provide more accurate measurements of the trunks themselves. And then the leaf on would actually produce better measurements of the crown height. To do this, the next is fusion. Because these are two separate data sets, I feel that there could be some benefit if you actually take those data sets and merge them together into a single one. So that way you can actually have the structure of the trunk built in with all the trees, the branches, and the crown on it. So I have two thoughts on that one. One is the tree height is going to be better measured with that fused data set. And two, that the tree diameter will still actually be better measured with the leaf off. It's just reducing some of the extraneous noise and actually trying to get into the tree itself. The third are the neighborhoods. Different types of neighborhoods have different conditional aspects to them. So I think that's one of the things that will be addressed in the study. And the spacing, size, lots of different factors are in these neighborhoods. So I feel that the areas with newer development, just because of the structure of them, will be easier to actually identify. We'll talk about that here in a moment also. And then finally is automation. This is going to be a work of love, I guess you could say. There's going to be a lot of hours doing it manually, which is what I'm going to start with. But I feel there is a way to automate that process. And I feel that if we do the automation, I will get better results by doing it by hand, but I think the automation will greatly speed up the process. So that's one of the things I want to look at and see how that affects each other, or how that those compare. So those are some of the concepts going with the research question. Now going into the urban forests themselves. Urban forests are different from natural forest systems. They have their own unique characteristics. They tend to be a really complex mix of different ages, species, and they're spaced by where people want them. So they tend to appear in clumps, and they're spaced according to actual people's desires as opposed to natural progression. And the species selections are chosen for ornamental and visual aesthetics as opposed to just the actual trees that should be in that natural setting. And then there is that need for effective management. Again, you have to inventory these trees. So up here we just have some images. The upper one is what you'd see in just a natural forest. A more homogeneous mix of trees, no rhyme or reason to the spatial planning, but they fill in every available space and it really looks kind of full. And then here is a picture of a neighborhood. Actually, it's the, which one is that? That's the Huntley Park area there. And as you can see, there are clumps and spots, and there is not natural design on that. Okay, so going into some of the methods used for the surveying. First is the ground-based field survey. And as I said before, this is done by hand. Someone's going out there and actually taking measurements. Trees are sampled individually, so you have to spend time on each and every one of those trees. The ways that these are typically done to get your height, you either use a height pole, going out there with a really long stick and trying to eyeball it to see if it is at the right height. And we also, the method of hypsometry. You take a little sighting tool and you use the distance to the tree and the angle to the top of the tree to calculate your estimated height. The second factor that I will be measuring, and usually measured, is the trunk diameter at breast height, and that is 1.3 meters by industry standard. The trunk height can also be used for a thing called telemetry. That is a set of calculations and equations that are used to estimate tree height from that diameter at breast height. And those equations are adjusted for different species of trees and the location that they're in. When you do the field survey, there are lots of additional characteristics you can gather, like health, basic overall standard of the tree, but it takes a lot of time. You have to be out there and you have to do it. Next, we'll look at airborne laser scanning. This is done from an aircraft, usually either a plane or a helicopter, and you can scan large swaths of area at a time. So you can do large characteristics, large imaging projects. This is a really beneficial thing, and it's really great. But, so LALS is also known as LiDAR, light detection and ranging, and basic principles behind it is laser pulses are emitted from the aerial vehicle. They bounce back, and the time elapsed is used to calculate distance. The angle that the beam is sent out is used to calculate the angle of the feature from the aircraft. And so by combining those, you can actually get a location. When those points are returned, those are added together, and we actually start building what's called a point cloud. It's a three-dimensional representation of individual points in space. And from those, you can extract surfaces and develop features. It does have a high spatial accuracy. Literature says it's usually between 1 to 6 centimeters in vertical accuracy. And here's just a little image of someone scanning. Another benefit of ALS is it does have limited penetration through your canopy cover. So even if your canopy, if your ground is not completely visible, some of it can actually penetrate through, and so you can get that ground height, which does improve your tree estimation abilities. It is being used quite frequently now in tree height estimation, but some of the problems with ALS is what's called the lower limit threshold. The sensors only pick up returns that meet a level of intensity. So there's lots of returns that can actually get back to the sensor that are not being read. And due to this, the point density in returns can be very low. And that's the points per square meter. The final thing is the cost, like I mentioned earlier. DeKalb County had a tree survey done in 2009, and it cost them $179,000 to do that survey. So that's not a line item budget that they have very frequently to expend on something like this. So that's one of those limitations of the ALS surveys. Now moving on to unmanned aerial vehicles. These are something that can be with a small or a single person crew. I've been doing most of this myself. I have had someone out there with me a couple times. So your personnel expenditure is very low. Your flight parameters can be adjusted on the fly to suit whatever condition you need. You can change your flight height and image overlap. You can change the resolution of the camera, or you can change some of the imagery in the camera. The flights can be repeated as needed. Like if you don't get a good return on one, I can go out and fly some others. So I'm going to have to repeat a couple myself. That's one of those things that you can do as needed. And the imagery is very high resolution right now. I think the unit I'm using is 12 megapixels. I'll get to that in a moment. But that means you can have large amounts of this data coming in. You can have huge volumes, and it can be either still frame or video record. So these are really beneficial characteristics. Now, photogrammetry, which is the process of using 2D images to build a 3-dimensional image, is what the processing that I'll be using is built off of. Here's a nice little image here. Basically, you take images and you identify individual points within those images, and then you measure the adjustments in angle and size or height within the image, and you can extrapolate that into a real-world image. A couple things you need to know to do this properly is your flight height or the distance to image that you're focusing in on, the focal length of your imager, and the scale that you're imaging at. Now these images are scanned for these identifiable points, and with that, you can actually build your model up. And this can give you a nice 3D representation of your image. There is an advancement from that called structure for motion, which is more of an advanced form of photogrammetry. And this was developed out of the computer vision world. They were trying to teach machines how to read items. And so they figured out that you can use larger sequences of these images to extract these features. So what you do is you basically take a large group of images and you scan these images for key points that repeat throughout sequences. And then just like in photogrammetry, these spatial shifts in these relative images are used to build up your 3D surface, and they can get these point clouds, which can be used then to visualize these surfaces. With photogrammetry, you get these point clouds that can be processed just like you would with LiDAR tools or ALS tools. So there already is a package of materials in place that's ready to process these points. And the best thing about this is you get a very, very high point density. The images I've taken already and I've started roughing out, I'm getting over 1,000 points per square meter. That's a lot of good resolution into it. Okay, so in structure for motion, this is actually an image from the processor that I'm using. It's taking all these groups of images and correlating to each other, and you can see the point clouds being developed underneath it. So you can take massive amounts of these images together. This image right here has, I think that's 3,000 images in that group there. About 3,000 different images that were built into that section. So it's a lot of imagery that you can process. It does take some time, but it is really kind of fun. Okay, so structure for motion is actually starting to be used for tree height estimation, but right now it's mainly being applied in natural forests and in agricultural settings. So it's being done in quite a few places. The usage in the urban forest setting is minimal. I've been just doing my background research. I've found very few places that it's actually been done in an urban setting. There are some parameters that are limiting your structure for motion, your output, and these are basically part of your image quality. You know, the things that you think about are your camera lens, your pixel depth and resolution. You have to have enough overlap because it depends on seeing the same point in multiple images. So the more overlap you have, up to a certain point, the better. The height above ground level, because the resolution of your camera is finite and fixed, there is a sweet spot of resolution. And the angle relative to the ground, how you're imaging the ground itself matters. Then there's the environmental factors. Illumination and angle, the illumination angle relative to the object. So how much light and where the shadows are. Because those can play a big role in your actual final image, in your final process data. Okay, now, once I got this image, what do I plan to do with it? And I plan to run a couple tests on it. I want to test the structure for motion against the ground-based field surveys and the airborne live laser surveys. And the tests I plan to run are a root mean square error to find out deviation between the two, and then the linear regression, so I can find out my R values. So with these two, I should be able to get a good comparison. And these are the methods that have been used in most, if not all, the studies that I've seen. Some of the studies we've seen in ground-based field measurements compared to UAV. In an olive grove, so in a forest setting or agricultural setting, they're getting between 0.33 meters and 0.39 meters in difference. So that's not bad, but it's actually decent. In a mixed forest, in a natural forest setting, though, they're getting between 3 meters and 3.08 meters. So there's a lot more variation there in that natural forest setting. Now, compared to airborne laser surveying, scanning, they're getting 1.3 in a eucalyptus forest, and then I saw between 1.6 and 3 meters in a couple different temperate deciduous forest settings. So there is some material out there, and there is that range. So I think with these tests, I'll be able to actually get something that I can compare and contrast to other results out there in the field. And these are just some of those surveys I was actually talking about. You see it's being used all over the world. We've got Finland, Spain, Maryland, Australia, Czech Republic. So it's out there. People are using it. But these are all either natural forest surveys or agricultural surveys. And these are where basically most of the imagery or the data is coming from. So hopefully mine can add something in that urban forest to this breadth of data. Okay, our study area. It'll be right here in the DeKalb area. I will be using a sample set that was identified by Dustin Bergman when he did his thesis here a few years ago. There are two main sampling areas. There is a historic area, which is up in this area here, and the newer development area here. These two different zones will actually present a range of conditions. That they're not the same. There's different tree structure, types of trees, patterns of planting, and the sample will only include the public trees. Those are the trees on the right of way or in public spaces. So will not be any private trees measured in this. Now, if we look at the historic area, this includes the Elwood area up here at the top and the Huntley Park area down here. The survey group that Dustin did had 710 trees, and I will resurvey the same trees because he gives me a ready source of comparable information. These are larger, more established trees. These are trees that some have been there for 100 years. Others have been changed, but it is well established. There is irregular spacing here because of the natural progression of trees that we said. Trees have fallen, trees have been cut down, trees have been replanted. So it is not a uniform distribution. So this should test the ability to identify the trees in it. And then there's also a heterogeneous mix of species. It is not a single species there. You know, people over time, oh, I like this type of tree, I'm gonna plant this type of tree. So there's been much more time for people to actually get their own human anthropomorphic mix into it. Whereas the new development areas, which are the Knolls area and Kensington Point here, there's 325 trees in this section that will be surveyed. These are newer trees. They're new growing, they're smaller, and they tend to have more regular spacing. Because with the new developments, people are still like, yep, put one here, put one here, put one here, nice, neat patterning. And there is more of a homogeneous mix of trees. Because we've seen things that do not work well around here, like Dutch elm and some of the other trees that have had problems. People stopped planting those trees. So now there's a more uniform mix of trees being planted. Okay, so we're gonna look at the data sets now. The first data set, which will be a base layers data set, is going to be that ALS data set. Like I said earlier, it was acquired in 2009. It was flat altitude was 1,400 meters, so it's not too bad up there. And when you look at the data itself, it only had an average of 0.68 points per square meter. So that's where that spatial the low resolution comes in, because you're getting, you know, maybe a 1 to a half a point in each meter square. So we'll talk about that in a second. So what that does, though, is it means when you're resolving a tree, you just get whatever return happens to come off that tree. And for an entire tree canopy, you might get 30 to 40 returns off that tree canopy. And that's not enough to get a great, accurate measurement off. It's, well, take it back. It would be a nicely accurate measurement, but it's only on that point. So you don't get the whole tree cluster. The vertical accuracy of the DeKalb survey was at, according to Sanborn, was at 6.9 centimeters, the mean squared error. And the horizontal accuracy is 1 meter, so things can be shifted left or right. It was georeferenced to state plane NAD, state plane East Illinois, state plane East NAD 83, which is the same one we would use for everything. And all the following data is being referenced to that LiDAR data set. It's nice, well-established, large coverage area, and the accuracy is pretty good. So we will, everything else will be merged onto that data set for a single point of reference. For the ground-based data set, the trees are individually measured. They were sampled for height and your DBH, your diameter breast height. They're recorded using the laser ACE, this little doodad there that you sit there and you sight through. And the trunks were manually measured with a, I believe it was a tape, a measuring tape. So simple, but takes a lot of effort to do that. Okay, here's just some general information about it. The Bergman sample, there was a total of 1,035 trees in his field sample section. It was sampled during leaf-on conditions, so you only had the one condition of sampling. There was a subsample of 10 trees measured using a total station to test out the accuracy of his methods. And his comparison between his comparison was a 0.07 meter mean squared error for his measurements. For my sample, I'm actually going to go out and take a 50 tree sample to compare to his original sample to account for things like growth since that last data set was done, any sort of variations that may be out there that you just can't get from any other way, but actually going out there and sampling. And these will be a representative sample. I will try to pick all the different types of trees out there and as many different conditions as I can get within that sample. And some trees will grow faster, some trees will grow less, and I want to have a nice sample. So some of the work I've already done, this is just a rough sample. In some of my preliminary work, you see some of these trees here. His height sample was 15.88 meters, and I'm already getting about 20.73 meter. So trees have grown. And I have to actually go out and do a little bit more measurement, but that's just some of my rough data. And I'll improve on that as I go along. So just in the sample that I've looked at, there is some change. Okay. And that also goes the other way. I'm actually getting some values that are lower than his value. And that's something I'll have to actually look at and see what could be the cause of that. Because he's citing with the hypsometer, he can only cite, it was only cited to where he could see the crown at. So one thing I hope to improve with this method is being able to better judge that surface of the tree canopy. Okay, so now my data set for my UAV, I will have two sample conditions, the leaf on, leaf off, and this is actually pictures of the same location. Same location, and you can actually see in the leaf off, you can barely make out the trees, but yet in the leaf on sample, the trees are visible and readily apparent. So I think that will be some interesting results. In the leaf off sample, you can actually see the trunk of the tree. You can see the branch, you can see the structure. I think this will pay off very well in the newer or the older areas where you just really can't tell where the trees are. So these two will be the base sample sets. Then I will get a merged sample set of putting those two together. And then I will have another sample set which will be from my automatic algorithm. And that's one that I will be building and developing to plot our data. So the unit I'm using is a DJI Mavic Pro. I fly at a height of 80 meters AGL from the point of launch. That is one of the keys. It is from the point of launch. It does not adjust to the terrain as it goes over. So all my heights will be from there. The camera angle is about 70 degrees on the camera angle. The resolution of the camera is 12 megapixels, which produces a very nice image, as you saw from that previous slide. I run a 80% overlap, and I fly in a double grid pattern to try and get, so that flies this way, and then that way, and that way. So that way I can get the full volume of the tree in my imagery. Okay, my data flow. Right now, I've been processing on a Dell PowerEdge server. It has 2 Intel E5 2670s. I'm running 16 cores, 32 threads on my processor, and I have 118 gigs of RAM in my server. So it seems like a lot, but these do take a while to process. The software I'm using is a Pix4D Pro Mapper desktop. It is a photogrammetry-based structure from motion processing tool. That will generate my actual point clouds, and then to analyze my point clouds, I'm using Cloud Compare, which is an open source point cloud viewer. So, yep, the workflow is collection, mosaic, taking the images and stitching them together. Then from those stitched together images, it does the structure from motion processing, which gives me my point clouds, which I will reference to each other and to that LiDAR set. Then I will go in and extract my tree data, and I will run my statistical analysis. Okay, so in the Pix4D software, the first step it does is it does an image mosaic. That's where all the flight images are arranged in their spatial origin, and it creates a single coherent surface image. From that, it takes those and it runs the structure from motion processing, and it gets us these, what they're called densified point clouds, just lots and lots and lots and lots of little 3D points with X, Y, and Z attributes. This is just a sample of one of the processes I ran. This one, for this unit, it took 5 days, 12 hours, and 44 minutes to run on my server, and the final output was 3.6 billion points. So it's getting a real good resolution, and I'm getting an average of 1,233 points per square meter, which is a big improvement over the returns you're getting from ALS. Yeah, these are just some images of, these are actual samples from that processing I just showed the stats from. These are not pictures, these are actually the point clouds. So as you can see, there's really good detail in it. You can pretty much see where almost the individual leaf structures are of the tree, which will allow me to figure out where the proper place to measure the height of that canopy is. So really, yeah, liking those. Okay, now the process for the manual extraction, I'm using Cloud Compare software. I will actually go in and manually measure these, the tree height and the trunk diameter, and the process that basically appears is, let's see if this, can you do that from your side, Tom? Or?
Try clicking on the image. It looks like it's
Up. Yeah, no, just there you go. So actually, you go in, you identify the tree. I select my tool, find the top of my tree, find the bottom of my tree, and there we go. I have a measurement. So that tree, it says, is from those points, it says about 12 meters tall. So I'll be doing this with all the individual trees in all 3 scenarios: leaf on, leaf off, and then in the merge scenario. So all 1,035 trees will be done manually 3 times for the height and the trunk diameter. Still running. Well, on that aspect, I've been timing how long it takes me to do each one.
Yeah.
It's 4 or 5 minutes each tree to get the height and the diameter. I'm doing it 350 minutes a tree. I calculate it's going to take me about 250 hours, if that's the pace I stay at, to actually go ahead and measure all these trees. Hopefully it'll speed up. And on that aside, we've looked at using immersion or virtual reality immersive environment to do it. I actually have a Oculus Rift that I'm going to be using to test out to do this, because there are some easier ways to do it when you're in that immersive environment. You can actually move around inside of it. The results I'm getting from that are so far pretty good. It's a little bit more difficult and takes some getting used to, but I think that should speed up my process being inside the VR environment. Sorry for that aside. Okay, continuing on. Did it freeze? Huh. I think the slide might have. There we go. Okay, well, that was the manual part of it. I plan to try and build an algorithm that will recreate my actions in a much more expedient manner. So the workflow for this is you have to load the point clouds and the tree locations. The trees have to actually be referenced within the point cloud itself. I'm going to need, sorry, Tom, you're sort of covering part of the slide here. Let me move you out of the way for 1 second. All right, you go in the corner. Okay, so the algorithm will have to establish the ground surface layer in the cloud itself. From that, then it can extract the tree height to crown. It has to identify the location of the trunk, which is one of the reasons why I wanted that leaf off condition, to try and find that trunk. Then it will measure the breast height on the trunk, so that 1.3 meters, measure the diameter at the breast height, and then export my data into a file that I can then run my statistical tests on. That should be my workflow for the algorithm. Hopefully, yeah, that'll be some fun. Okay, going on. Yeah, it seems to want to slow down right now. Come on. All right, there you go. Oh, same one. Basically, so with that data, we'll run the regression analysis, the root mean squared error test, and the comparisons that will be run are the UAV manual versus the ground-based field survey, the UAV manual versus the airborne LiDAR survey, and then the main one is going to be the UAV manual versus the algorithm test. So that way we can see just how well I perform compared to the computer, or actually how well the computer compares to my measurements. And, okay, and then the other aspect I would like to do is a temporal analysis. How much time does it take? Because one of the points of the project is not only is it easier to do, but that there can be some time saving in it. So that big test is going to be 3 different points. There's going to be the collection procedure. How fast can it be recorded? And I will try and contact Dustin to see how much time he actually spent on his field survey. But I'm actually going to count the time that it takes me to go out and measure my 50 trees and then extrapolate up from that point. So we'll see how long the collection procedures can compare. Then the data generation. There is no data generation time frame in the field survey. Once it's in your notebook, it's in your notebook or in your spreadsheet. So that'll be an added time to consider. And then it is the data extraction time. How long does it take me to get that data into a usable format? And there'll be 2 times for that. One will be the manual time. How many hundreds of hours does it take me? And then there will be the algorithm time, which is what we're really shooting for, where I believe the savings is going to come. In here, there's just a little bit of data. This is how long each one of these individual flights I've taken do. They tend to, for a full flight, usually is around 20 minutes or so. That's about the average battery length or battery lifespan of the unit that I'm working with. And then there's some spot fills that I did here also. Come on, let's go. No, that's one move. Oh, just jumped a bunch. Okay. Okay, so to wrap up, public resource monitoring is a very important task. It needs to be done. Cities, villages, organizations, entities, they all need to do this. And with our urban forest inventory, they need a method that is cost effective. And they need a method that is repeatable on demand. Because a lot can happen in 5 to 10 years in a city. You know, things can change. You can have more pest infestations. There's lots of things that can happen in that time frame where you need to know what you have to have. So I'm proposing my UAV method to monitor and inventory these tree data, which can be done at a local level. We will use regression analysis and root mean squared errors to show the differences between the method proposed and the current methods. And then finally, I will present a functional way of surveying, processing, and analyzing the data that we have here. And then we have the timeline of the project. It will move again. It keeps freezing. Sorry about that, everybody. Okay, so my timeline is November, I submitted my proposal to you. This month, we have the thesis defense, the proposal defense, which I'm doing right now. And then as soon as this is done, I will, actually after this class week is done, I'm actually gonna get out there and start doing my first set of field sample measurements, because these are off the trees. I can get some good leaf off measurements. I will go out and basically drive the streets to update Dustin's tree sample, see which trees are actually still there and what I'm working with, begin my data extraction process, to be fun. And that includes, measuring my tree heights and trunk diameters in the point cloud. I will be sitting for my FAA Part 107 test to actually become a licensed independent pilot, since actually it's into the research phase now. And there are some sections that I'd like to refly, because as time has progressed, I've become much more competent, I guess you could say, at using my drone and actually setting up the imaging process that I like. So there's some areas that I wasn't too happy with, so I'm gonna go ahead and refly those. And that's how we're gonna close out this year. And then starting in January, it's more measurement, more measurement, more measurement, which should take quite a bit. Other things like submit my application for degree. I think by about February, I should be actually getting into the process of the algorithm development. I should be comfortable enough in the process that I'm doing that I should be able to start programming or planning the actual computer interface for it. I think that's about right. Come March is when the big stuff starts to happen. I should be finishing up with my data extraction by then, I believe. I should be able to run my algorithm, and I should be able to start the analysis, actually seeing if this actually pans out. And at that time will be when I should start my final thesis preparation. Come April, data analysis should be completed. Any things I needed to change should have been okay. Continue my thesis preparation, and I hope to present at the Illinois Geographical Society annual meeting out in Dubuque. So I should be able to present there. By May, I'm going to finish I will try and finish my thesis. So I will actually be presenting after the end of the school year. It will be a summer presentation. Dr. Pringle and I were talking about that just to give a little more time, since I started so late and everything. I'm still trying to play catch up on my timing. And then if there's any sort of, I guess we really don't have comprehensive exams in the department, but come June, I should be ready to submit my final project to everybody, the final thesis, and be ready to defend. So, and then the final, submit the post-defense version of the thesis, and dance for joy and be thankful. So that's where we are at, everybody. And I don't think I took too much time. Sorry about that. I seem to be long-winded. All right. I'll give control back to you, Tom, or if you guys now time for questions.
Okay, I'm gonna